Right, so in this video, I'll continue discussion on the limit curves. I mentioned that the limit state surface used by the uniaxial material model is referred to as limit curve because it's only two dimension and it defines the limits and it's directly OpenSees to trigger warning for the failure if that limit is crossed here. Now, um, we need to understand the application of the limit state material model. So, um, the most important thing is um, the limit curve. For example, if we have failure, right, and if we have deformation. So there is a certain point which is important, which is called failure point, and I mentioned that in this region as well, right? That at certain point, the material that you are using, it will reach to a specific point where the if it is shear or any other response, it will detect its failure. So if there is no failure response, it will reach in elastic region. But since we are using a spring element in the combination with the beam column element, so we assume that there will be a pre-failure curve, and right, that will be pre-failure backbone curve. And when the failure occur, this will be the degradation in terms of definition as by considering it as a K definition here, right? KDEG, and then this curve, this will be the restraint. This will be the remaining residual strength of the given model. So um, now look at here in the previous videos I mentioned this as well that how the limit state material model can be used that will represent the uh, axial uh, the uniaxial material model to model the column shear failure, while the second uh, for the column axial failure. So if we are intended to use the model axial failure, the limit state material model incorporates coupling between shear and axial load after failure is detected, right? And if we want to model the column axial failure in all those steps, then we can further incorporate the uh, hysteresis curves by defining various limit state material models for our analysis. So, as soon as that failure is detected, we will look at the hysteresis response, that it will not go beyond that region and it will behave like this, right? And we at the end get the response of the curve. So we have that shear limit curve, right? and we have this pre-failure backbone curve here at this region, and we have the axial limit state here, and we do this by combining those spring element here. So how the slope is determined for the KD. I mean, if we are using OpenSees, how we can determine the degradation of the slope here. So that depends on the loading and unloading of the model. And if we have axial limit curve and we have shear limit curve, we got two points here. As I mentioned here, for example, if this is the axial limit curve, right, and this is the shear limit curve. So that slope can be determined based on the intersection point of these two curves, and we get this here. Then it reduces itself according to unloading branch here. So various cases can be combined in the analysis, and if we get the comparison of the response for strain hardening under shear failure, we get a very complex model, and we need to go to the theoretical background to then discuss the shear and flexible combined deformations here. So I'm not going to discuss those in further details uh, because it's a very complex topic in that sense. But the idea was to give a picture of how this model is working. Then further, we can combine the beam column element with the axial limit material model for the axial limit curves and uniaxial material, and we can get further material definition in our analysis. So this is the idea that if you are defining the material model, so this is how we do the analysis and the OpenSeas, and there's no practical example right now that I'm discussing here in terms of coding. So when I'm trying to deliver lecture on the modeling based on that sense, I'll be able to demonstrate uh, axial limit curve and all the other parameters in the analysis, and then uh, I'll be able to demonstrate how this works here. So I think now those definitions that I was trying to demonstrate here, that what are the limit curves and what is the shear failure and what is the limit state material, what is the empirical drift capacity, all those are included here, right? So in order to include that in the OpenSeas to STKO, you have to define the model, right? And then for element tag, since we don't have any zero length element at the moment defined, so the drop down menu is zero, none, and similarly we don't have any other nodes definitions or sets that we have defined here. So these I node tag and J node tags are not visible here to us. And here we can define the literal degree of freedom in terms of shear demand and as well as the other demands, right? And This limit curve section that only consider the limit curve that we define through shear limit curve or axial limit curve. If we define both, then both material can be defined. So this is a curve tag, and this curve tag has been incorporated here, type of the limit curve, and then the element tag. So for the beam column element that we consider, this is the transverse reinforcement ratio, area of steel divided by BH for the section. So this is the compressive strength. You should be careful about units that you are using. So let's say this is 35. Yield stress, let's say it is 450. So 3.5, 200, 60, whatever you want to use. This is the grass section area. For example, it is 12 by 12. Transverse steel reinforcement ratio. This is rho T. Transverse steel reinforcement ratio. Rho is basically used by ACI in a lot of cases. So let's say 0.02, and theta y is the yield rotation of hinge, let's say 0.001. Shear capacity of the column, if let's say you did calculation for the section and you find out the 45 psi, 4.5 psi with the shear capacity of the column, then unloading stiffness of hinge, uh, uh, if it is given here, that's okay. If it is not given here, this is basically the unloading branch that is required in terms of response. So you can decide this unloading branch from the literature available in the Ken Elwood code, and also you can do all these steps and combinations for the unloading branch and merging the shear spring response and beam column response to get the unloading branch as well. So let's say this is 12, and let's look into the plastic shear demand and define the plastic shear to be 5.5, right? So this is how you then define the limit curve for the rotation and the definition. In the next video, I will discuss the custom script definition, that how we can include or take a script in our analysis model and insert them inside your STKO environment. So I think after custom, then we have the random variables from the tickle script, and we can further discuss the other time series stuffs and all those things in our analysis, and we can do discussion on it as well. So these are related to beta random variables in OpenSees, so you can draw them for the test distribution data and other stuffs, and we can then define the constants, we can define the factors, the linear range, and the path and all those stuff. So I will discuss all these in detail before going to the physical properties. So make sure you uh, watch these videos and don't skip anything in the videos to get used to with the lectures, and then when you are practicing it, you will have idea of what you are doing in the analysis. Thank you so much for watching.